Hello, class. Today we're doing lesson number 5 in chapter 8 of exponents, and we're covering small numbers. And here we have a photograph. It says this remarkable photograph made with an electron microscope shows a virus magnified to about 1,000,000 times its actual size. This virus causes respiratory disease in human beings. The shape of the virus is that of an icosahedron, and the geometric solid, which is the geometric solid shown on the left of this photograph. And what's peculiar about an icosahedron is that you have 20 sides of equilateral triangles. And it's really neat, and you'll learn more about that in geometry. But nonetheless, let's continue reading. It says here, the virus is so small that its volume is only 0 point, and let's read all these zeros, 0.0000000000000000002 cubic centimeters. Now, it's hard to believe that something this small could be photographed or measured. Nevertheless, scientists must work with numbers much smaller than even the volume of a virus. And to do so, they usually express such numbers in scientific notation. Now, we have learned that a number written in scientific notation has the form, and let's put it up here on our board. It's going to be A times 10 to the b power. Okay, so that's a form, and we know that we have a number here, and we also know that a is a number that is at least 1, but less than 10, and that b is an integer. So how could we express? Well, a is greater than or equal to 1, right? And but it is also less than 10. Okay, actually we could write this another way. I can flip it the other way and put 1 here. Okay, so A is either going to be greater than or equal to 1, but it will be less than 10. And we've already discussed that in class in terms of why it needs to be less than 10, because you can only have one decimal point to the left, or excuse me, one digit to the left of the decimal point, and that digit obviously needs to be 1 or greater. So let's take a look, and it says, to see how a small number can be written in scientific notation, consider the numbers 4,000 and 0.004. So we have 4,000, which is equal to 4 times 1,000, which is equal to 4 times 10 to the third power. Okay, so let's take a look over here. Let's put it on the board. We've got 4,000. Okay, and that's going to be equal to 4 times 1,000, which is equal to 4 times 10 to the third power, which we know that 1,000 is 10 times 10 times 10, so that is 10 to the third power, right? Now, let's also, and we can also see that 1,000 has 3 zeros, and in this particular case, we've talked about thousands and millions and billions. You just simply count the zeros, and you know exactly the exponent in terms of its power of 10. Now, let's take a look at 0.004. And we know that this is 4 thousandths, right? So that's 4 over 1,000. And we also know that we can just simply write that as 4 times, let's get that 4 out there, right? It's 4 times 1 over 1,000. Okay, so just put my little comma in there so you can see. Now, typically I would not use commas. They're using them. When I express numbers, we can express 1,000. When you start getting into larger numbers, you definitely want to. So 1,000. When you're in that thousand zone, you're usually okay, but we're definitely expressing them here so you can see particularly the threes there, the 3 zeros rather. So now let's write that as 4 times 10, or excuse me, 4 times 1 over 10 to the third power. Okay, now we see how these look very similar, with the exception that in this case we're dividing the 1,000 into 1, and we also know, and let's write it down here, that when we express 1 over 10 to the third power, we know that we can express that as 10 to the negative 3 power. We've discussed that. That was I believe it was the third law of exponents, and actually it was the second law of exponents, and we know that we can just we can subtract, in a sense, the exponents. Let me bring that over to this side of the board. 1 would have been 10 to the 0 power. Okay, anything to the 0 power is 1, and then we would have had 10 to the third power, which we could express this as 10 to the 0 minus 3 power, which means this is 10 to the negative 3. Okay, so we know that, and again, this is 1. We just simply change the expression so that you can have the same base, and we were able to now express this as 10 to the negative 3 power. So, in the first case, the decimal point, we're back here to our text. The decimal point has been moved 3 places to the left, and the exponent is 3. Okay, so we see here, we move the exponent 1, 2, and 3. Okay, we're here at the top of the board. Okay, so we moved it over 3, and in this case we moved it over, that's to the left. In this case we moved it 1, 2, and 3 to the right. Okay, as we read here. Alright, in the second case, the decimal point has been moved 3 places to the right, and the exponent is negative 3. These examples illustrate the relationship between the number of digits and the direction in which the decimal point is moved, and the exponent when a number is changed from decimal form to scientific notation. If the decimal point is moved n places to the left, the exponent is n. And if it's moved n places to the right, the exponent is negative n. If the decimal point is not moved at all, then the exponent is 0. Using this relationship to express the volume of the virus in scientific notation, we get, and we look here, we move over 17 decimal places. And we have now the expression 2 times 10 to the negative 17 power. So we have 2 times 10 to the negative 17. Now why did we not move it over 16 and have 0.2? Then it would not have satisfied this particular requirement for scientific notation, that it needs to be greater than or equal to 1. So we have to go all the way to 2, to the right of the 2, and we now have 10 to the negative 17 power. Now here are more examples on how small numbers are written in scientific notation. And we have here 3 is equal to 3 times 10 to the 0 power. We know that 10 to the 0 power is 1, so we can express a number such as 3 in scientific notation. We just need to remember that we're multiplying by 1, and that we can express the power of 10 as equal to 1 by simply putting it to the 0 power. We also have 0.08 is equal to 8 times 10 to the negative 2 power. We see that if we simply had moved over the decimal point to the right, we would have moved over 2 spaces to the right, which is the negative direction. It would have increased the exponent, or decreased it, let's say, by 2. And then we have 0.000027, and we see that the decimal place was moved over to the right 5 places. And again, moving to the right, we've gone to negative 5. Now, the way that they show it is a direction, left or right. All right, we already saw that. If it's going to be, if you move to the right, all right, And it's okay. We're going to show this to you in two different forms. And it's okay to look at it in either way. Whatever connects best with you. We can move to the right or we can move to the left. That's our option, right? And of course, we don't move at all. And then we know that that's a 0. But if we move to the right, that means it will be a negative, a negative n. If we move to the left, it will be a positive n. I'm going to put the positive. It'll just be n. It'll be the number. So the number of decimal places that we move will determine. Now, the other way of looking at it is, I'm going to write over here, if we take 0.004, okay, and we know that this is times 10 to the 0 power, right? As it stands, we can express this in scientific notation. It's 10 to the 0 power, which is 1. Now we're going to increase the value of this number 1, 2, 3 by moving it 3 decimal places, and we're going to create another number, which is 4. Now we've increased, in a sense, the value on this side because we've gone from 0.004 to 4. Now, in order to do that, then we need to decrease the value on this side, which means we need to go downward the number of decimal points. So we moved over 1, 2, 3. So we would decrease the exponent by 3. Okay, which was 0, so now it's negative 3. So it's maintaining the value. We know that this is equal to 0.0 or 0.004. For this to remain the same number without changing its value, if we're going to increase the value on this side, we must decrease the value on this side. And we can simply see that. Let me clear up the board here. And it's simple multiplication, and we can use a simple example. If we were to have, let's say we're multiplying, get my pen back, 4 times 1. Oh, my pen is much thinner. Let's get the pen back the way it should be. Okay, so we have 4 times 1. Okay, now with 4 times 1, we know that's equal to 4. Now what happens when I decrease 4 to 2? Well, it means for this to equal to 4, this side's increasing, is it not? Yes, it's 2 times 2. And if I were to decrease this any further to 1, this would have to be 4 for this to always equal 4. So remember that when we're looking at scientific notation, we're trying to maintain the same value as we did here. Okay, we maintain the value of 4. Now, in scientific notation, we may be looking at it in this form, but it does point to an actual value that we know that we can write with all of its wonderful zeros or decimal places over here. We want to maintain the value, so as we did all of this, we did not change its value, we're just changing the expression of the value. And in this, we also did the same. 4 times 1, 2 times 2, and 1 times 4. These are all 4. So we did not change the value, though we changed the expression. And the same thing we do with scientific notation. We're taking, for instance, an expression of 0.004, and we want to change it to, well, we want to change this side of the expression to 4. Similarly, we change 4 to 1, right? So we change the value here, which means that this value must also change. So that's what we're doing over here. We had 10 to the 0 power, which we know is equal to 1, okay? But now we're going to change this to 10 to the negative 3 power because we raised this to 4. And we have that right here, okay? What is 10 to the negative 3? Well, it's 10 times, 10 to the negative 3 is 1 divided by 1,000. So just remember that we maintain the value but we changed the sides of that each side of that multiplication sign so that we maintain the same value. So that's really the purpose in changing the exponential or the exponent, is to maintain the same value.